Imagine nothing, complete nothingness. It's hard, right? Well, it's even harder to realize such an absolute emptiness. So let me turn on the light and tell you more about darkness. If you went to outer space, where temperatures are incredibly low, just 2.4 degrees above absolute zero, far, far away from any star or planet in the intergalactic nothingness, you would still find a tiny glimmer, the cosmic microwave background radiation, which is the relic of the early age of the universe. In modern scientific labs, as the one which I'm standing in right now, in the Quantum Optoelectronics group at ETH Zurich, we can reach temperatures 100 times smaller than the one in outer space. In dark fridges, where almost complete nothingness is achieved. And yet, you would still be amazed to find something: the quantum vacuum fluctuations. I am Lorenzo, and I'm an experimental physics PhD student. In this video, I will guide you through the exciting discovery which our team, together with my colleague Josefine and Enkner, and under the lead of Professors Jérôme, Faist and Giacomo Scalari, have made. Vacuum fluctuations manifest their reality on matter, and they can be used to improve some very fragile quantum states. The electric current which flows in our electronic appliances consists of a stream of electrons, tiny particles which bear negative charge, whose direction is usually aligned to the electric field 1. If you take a battery and connect it to a flat piece of a conductor, electrons will go from the negative pole to the positive one. In 1879, Edwin Hall discovered that if in addition to the electric field of the battery you add a perpendicular magnetic field, the electrons will not anymore go in a straight line, but rather will be pushed towards one side of the conductor. The effect was named after him, the Hall effect, and it finds a lot of applications nowadays. One cool one is the speed sensor mounted on the wheel of a car, which makes the anti-lock braking system work. The accumulation of electrons on one side of the conductor establishes a potential difference with respect to the other side, the Hall voltage, which is proportional to the strength of the magnetic field. As you may have noticed from the previous animation, the magnetic field is actually forcing the electrons to perform a circular motion, with a tighter and tighter radius as the magnetic field is increased. In common conductors, which contain a lot of impurities, you usually don't see any consequence for this quirk phenomenon. The reason is that the electrons cannot close the circle before hitting an impurity and starting to perform another interrupted circumference. During the 20th century, a lot of improvements were made in semiconductor fabrication to reduce the amount of impurities and to achieve extremely high-quality materials. So, when in 1980 Klaus von Klitzing stuck a piece of extremely high-quality conductor inside a fridge similar to the one we have at ultra-low temperatures and in a magnetic field, it came as a surprise that the Hall voltage was not anymore going in a straight line, but rather it showed steps, spanning a broad range of magnetic field and possessing a very precise value of the Hall voltage. Von Klitzing would go on to win the Nobel Prize for his discovery, and the very precise constant is named after him, the von Klitzing constant, which is still used for calibrating the resistances inside our electronic devices. The reason why the Hall voltage shows such precise values is explained within quantum mechanics, and indeed these values are said to be quantized, and the effect is called the quantum Hall effect. The gist can be a little bit understood by thinking again about the circular motions of the electrons. On the edges of the conductors, the electrons cannot complete their circles because they are bouncing against the edges, and this forces them to go only in one direction on one side and in the opposite one on the opposite side. When we change by a tiny bit the magnetic field, we are not changing these currents on the edge, but we are rather changing only the amount of electrons which we can put inside the conductor, which are stuck in their circular orbits. This means that we cannot change the Hall voltage. Light is a wave, an electromagnetic wave to be precise, whose color is determined by its wavelength. The shorter wavelength that we can see with our eyes is the violet color, while the longer is the red color. Still, what could increase even more this wavelength to reach the microwaves, which are the same kind of waves that we find in our ovens and which cook our food. But light is not only a wave. It's also made up by particles, the photons, and so a complete description of its behavior must be given in terms of quantum mechanics to take into account both its natures. Quantum mechanics then predicts that even in complete darkness, so when no light is present, there are still fluctuations in the electromagnetic field, the quantum vacuum fluctuations, which I was mentioning at the very beginning of this video, and which come about because due to quantum mechanics uncertainty, electric and magnetic energies cannot be both zero at the same time. Of course, we cannot use vacuum fluctuations to harvest energy. That would violate energy conservation. But we can still see the reality of vacuum fluctuations in experiments, for example, the celebrated Casimir effect. If you take two conductive planes facing each other in complete emptiness, they will be attracted by a force originating only from vacuum fluctuations. And these vacuum fluctuations also can be seen in a more mundane situation. The geckos owe their incredible grip on vertical surfaces to the Casimir forces acting between the settle pads on their feet and the walls. The quest to achieve new functionalities in quantum materials, which I was talking about in a video that I posted almost 1 year ago, has explored in the past decade the possibility to use vacuum fluctuations to modify material properties. Only recently, though, some experiments have shown the actual capabilities of vacuum fluctuations in material systems, and I am proud to say that our group is one of the first in the world. In our research, which was recently published in the Nature journal, we have considered very fragile quantum states, the fractional quantum Hall phases, which are a much more complicated version of the quantum Hall effect that I was explaining before, and we have investigated how they are modified by the influence of vacuum fluctuations, whose strength we could remotely tune. It was an experimental tour de force, actually started some years ago by my previous colleagues Gian Lorenzo Paravicini-Vagliani and Felice Appugliese, and which finally Josefine, Enkner and I managed to perform to such a precision to show how these fragile quantum states can actually be made more robust by the influence of the vacuum fluctuations. Together with our theory colleagues, Dalin Boriçi, Cristiano Ciuti, and Nicolas Regnault, we understood the mechanism responsible for this improvement, which amounts to a cavity-mediated attractive interaction between the electrons. To put it in simple words, these vacuum fluctuations can bring electrons together, giving rise to a mechanism which, in our wildest dreams, could maybe one day offer a new way to achieve superconductivity. So what's the deal with this result? Well, if you are a curious person as I am, you will just appreciate the beauty of a scientific discovery which opens up a novel way to understand how matter interacts with light, or rather the absence of light. But with no doubts, our work represents a huge achievement in giving evidence of what can be actually done with vacuum fluctuations and also their limitations. Indeed, to achieve such a clean and precise result, we had to use extremely high-quality materials, grown here at ETH Zurich by our colleagues Christian Reichl and Werner Wegscheider. And many months of measurement and data analysis were needed to rule out spurious effects. But as I always say in my videos, science is a collective endeavor which begins with understanding nature and only afterwards can give new technologies which can improve our lives. And for sure, the promises held by this material engineering with vacuum fluctuations are outstanding. This was it. I hope I could at least convey the excitement we share for this discovery, and of course I will be happy to answer your questions down in the comments. Let me thank again my colleague Josefine and our supervisors Jérôme and Giacomo, especially for having me in the team and for the great time we had while doing this experiment. I will never stop telling you how fun is doing science. Thank you for listening, and see you in the next video.